Hello, this is Concrete Path. Uh, Today's lecture is about combined stress, and before that, we have one problem related to one of the final problems related to that of torsion. That is the concept of uniformly varying torsion. Uniformly varying torsion. So you have this cantilever shaft, we can say, and it is subjected to uniformly varying torque, similar to that of a cantilever beam subjected to uniformly varying load, and W at the end. W is maximum at the fixed side and 0 at the free end. Similarly, we have this varying intensity of that torque. So we say it's increasing in the linear fashion. So here the intensity is 0 and maximum it goes to some value of T0 kilonewton meter per meter. So the variation is somewhat in a linear fashion. So I would say this is some variation of that torque intensity 0 to T0 kilonewton meter per meter. Then would say what is the intensity at any x from the free end. So at any x from the free end, there would be some intensity of Tx. That Tx would be equals to T0 for length of x, L I need for length of x. So this is your intensity of that torque. That's also we can say rate of change of torque. Dx. So I would say dtx by dx. Now I would say I need to calculate the how much torque that support takes. Torque developed at let's say this is A, this is B. Torque developed at support B, and we would say what is the theta developed at A? What is the theta developed at A? So I would say we have the equation for the torque, that torsion formula for the theta. I would say theta equals to TL by GJ. But based on this one, uniformly varying torque, we say your torque is a function of x, so it's varying with x. And similarly, if it is varying with x, so we can say you take some strip at some x, you take some strip of dx at some x, there would be some value of torque dx, and it would have some length of dx, and you divide by gj, it would give you small theta contributed by that strip subjected to that value of dx. Now similarly, this is your this part, you got it as a small torque, small twist, small angle of twist. Now if I want to calculate that torque at the support, at this support, that at x equals to L, what is the torque? So I need to convert it in terms of torque. If I write that torque at x equals to gj d theta by dx. So you got this equation. But your torque is also unknown, and theta is also unknown. So these two we have unknowns. But I know torque intensity. That's Tx, small tx. So if I say that dou Tx, what is the dou Tx by dou x? That's we can say Tx, and that would be equals to gj dou T d2 theta by dx2. Can we say that? So once I got the equation in terms of torque intensity, and if I substitute the value of torque intensity, that is equals to that is a critical point for here for this problem. That is that T0 x by L. So once I got the function of Tx in terms of T0 x by L, in terms of function of some T0 x by L, so I can now get from this intensity, I can get now torque at any x. So if I integrate it, now I would say, which implies that t at any x equals to x equals to integral tx, that equals to gj integral gj d2 theta by dx2, that equals to integral t naught x by L. If I say that, and I would say the function of the function of torque at any x would be equals to gj and d2 theta d2, I would say d theta by dx, d theta by dx, that is equals to t naught some x squared by 2L plus some constant of c1. So I got this equation that function, this is the function of torque equations. I would say this is your equation, torque equation for torque at any x, torque at any x. So based on this one, if I apply that boundary condition, that if I apply boundary condition, if I apply boundary condition, what is the boundary condition we have related to torque? Can you know? Can you guess what is the boundary condition from the problem? Boundary conditions. So I would say at this point we have that free end, so torque here would be 0. Torque developed here would be 0, and maximum torque we have here. So I would say torque at A would be 0. That at x equals to 0, your torque equals to 0. So that means your torque equals to 0. That means your this part, this is your function of torque. So this part is equals to 0. That equals to t naught 0. That part goes to 0 plus c1. So c1 goes to 0. And similarly, if you want, if you're not, now if we need two variables, we need two unknowns. We have two unknowns. That is, one is your theta, and next one is your torque at any x. So but we have based on this equation, we have two unknowns in one equation. We have two unknowns. So if I write that, if I integrate it once more, similar to that of that Macaulay's equation and double integration. So if I integrate it once more, I would write integral of gj d theta by dx equals to integral of t naught x squared by 2L plus c1 integral. If I integrate it once more with respect to x, I would get gj theta equals to t naught x cubed by 6L plus c1x plus c2. So we know that c1 was equals to 0, so c1 is 0. Then we can get the value of c2 for one more condition. So one more condition is that theta at the fixed side is equals to 0. Theta at fixed side is equals to 0. So that means at x equals to 0, at x equals to L, your theta is 0. So if I substitute that, that means 0 equals to t naught L cubed by 6L plus some c2. So c2 value we got, so we got some value of c2 equals to minus times t naught L squared by 6. So I got this part. Now I would say, what is the theta? Based on this one, I can get the value of theta. At any x. So if I substitute that, now the equation becomes that gj theta equals to t naught x cubed by 6L plus some c2 minus t naught L squared by 6 minus t naught L squared by 6. So if I say what is the theta at the free end, that is at x equals to 0. So I get a value of that minus t naught L squared by 6 gj. So this is your theta at the free end. And similarly, if I substitute that, what is the theta at the fixed end? Theta at the fixed end, that means at x equals to L. So if you substitute that, that means theta would be 0. Theta at B would be 0. Now, if I now calculate, if I want to calculate what is the theta at the fixed side, based on that, because C2 is 0. So if I have this equation now, that value of C1 is equals to 0, that means torque at any x is equals to gj d theta by dx, and that value equals to t naught x squared by 2L. So if I say torque at 0 would be 0, torque at L, that means torque at B at x equals to L, so torque at L would be equals to t naught L squared by 2L, that is t naught L by 2. So you got this value of torque at the I would say torque value at the fixed side. Now same problem, if I take that same problem, but I keep both sides as fixed. If I keep both sides as fixed, let's have that also. Let's keep that both sides as fixed. Let's say this is your shaft. and it's fixed from both sides. Now same loading, same value of torque, that's uniformly varying torque. Same torque, that's uniformly varying torque. Let's say this is your line, reference line. So this is your increasing uniformly varying torque, UVT. Intensity, maximum intensity is T naught, kilonewton meter per meter. So length is L. I would say this is your A and B. This is A and this is B. You need to get what is the torque developed at A and what's the torque developed at B. And you would say, based on that condition, we say that theta at the A equals to theta at the B, that is 0. So we have these boundary conditions now. We know that boundary conditions that theta A and theta B would be 0. So similarly, we can say now, we can derive that equation. We say you take some strip dx. There we have some small d theta. D theta equals to torque at that x dx by gj, and I would say dx equals to d theta by dx and gj multiply. Then I want to convert it in terms of that intensity, torque intensity. So based on that, I would say that dou tx by dou x, that is equals to t naught tx, that is t naught x by L, that is dou 2 theta by dx2, d2 theta by dx2 gj. So I got this equation. Now I got that tx as a function of small tx. So I'm going to integrate it again. So if I integrate it, I would get that integral tx. Forget this part because we want this part. This is our main part here. So we're integrating this part now. T naught x squared by 2l plus some c1, and that is equals to d theta by dx gj. I got this equation in terms of torque. So I got the equation in terms of torque, and I would say I don't know the value of torque. I don't know the boundary conditions, that what is the torque at A and B. So I don't know. So but I know theta. So if I convert that in terms of theta, so I have to integrate it once more. So I would say integrate it once more. That means T naught x cubed by 6L plus C1x plus C2. That is some value of theta gj. So if I apply boundary conditions that theta equals to 0 at x equals to 0 and x equals to L, so I know that theta is equals to 0 at x equals to 0 and x equals to L. So if I go from here, this side, that x, I would say at x equals to 0 and x equals to L, your theta is 0. So based on that, I would get an equation that 0 plus C2 equals to 0. That means C2 equals to 0. And similarly, I would once more get that T naught L cubed by 6L plus C1L plus that is 0 plus that is 0. So finally C1 is equals to minus T naught L square, T naught L by 6. T naught L by 6. I got this. T naught L by 6 C1. T naught minus times T naught L by 6. So I got that C1. I got this C1 now. So I got this equation of C1. So if I say what is the theta at any x now, if I write that equation now, so this was your equation of the theta. If I say that theta equals to some value of T naught x cubed by 6L plus some value of C1, that is equals to minus T naught L by 6 and some value of x divided by gg. So if I say theta at 0, that would be equals to 0. Theta at L would be also 0. So but you can get at any particular x, you can get the value of theta based on this equation. And if I want to calculate what is the torque at any x, what is the torque developed at any x, so I have this equation. The torque developed at any x, would be equals to, so torque at any x equals to T naught x squared by 2L plus some value of C naught, that C1, value of C1 was equals to minus T naught L by 6, So I got this equation. If I say what is the torque developed at x equals to 0, that means some value of T naught L by 6. And I would say what is the value of torque at x equals to L, that is equals to minus, that is T naught L squared by 2L plus minus T naught L by 6, that is T naught L divided by 6 minus 2 by 12, that is 1 by 3, that's 1 by 3, that's positive 1 by 3, T naught L by 3. So torque developed at the support B, that is more as compared to torque developed at A. Here the torque developed, so the I would say the direction of that torque is in this way. So that's clockwise, so pointing towards the support A. So if I make the line diagram, so there are some small torques, uniformly varying torques, and finally there would be some value of TA, that is T naught, L by 6, and here would be some value of TB, that's T naught L by 3. So this is your line diagram. So this is the end of that problem. Now our main topic for this lecture is that combined stresses. So we say that we take general loadings, we take multiple loadings together, and there we have concept of combined stresses. So if we have this one, that's a beam, simply supported beam, and you apply a concentrated load P at the mid span, and you take few points A, B, C, D, E. Similarly, if you took from the other side also A, B, C, D, E, but you call it as A dash, B dash, C dash, D dash, E dash. You want to say you represent the state of stress on these points. Write the state of stress on these points. So we'd say you have this point load, there would be some bending moment PL by 4, and here would be some moment of M, here would be some moment of M dash. But the bending moment diagram is positive, that means sagging, that means top compression, bottom tensile, top compressive. So above the neutral axis, so the neutral surface would be somewhere here. So on the CC, I would say there will be some neutral axis. So there might be some section, I would say this is your neutral axis. So the point C is on the neutral axis. So that means points above will face compression. So points A, B, C, D, E. So A point is having a compressive stress of M by Z. This point is having stress of My by I, and this one is having stress of 0. And A and B is having compressive. D and E is having tensile. This one is M by Z, and this one is your My by I. So you got this one. Now the thing is that what is the effect of that shear stress? We know that shear stress variation. The shear stress variation along the section is in this form: parabolic variation. That means shear stresses at A and E is equals to 0. Shear stress at A and E is equals to 0. This is direct shear stresses. And if we talk about point B and point D, they have same value of shear stress. That's some value of VA y bar by IB. They have some value of VA y bar by IB, and maximum would be at the neutral axis. Tau neutral axis is maximum tau. That's tau at C. That's some value of 1.5 tau average. So I would say what is the direction of that tau? Is it positive tau or negative tau? So for that, I would say, what is the shear force at that location? So if I make the shear force diagram, I have this shear force diagram. There is some P by 2 and there is some P by 2. This is minus, this is positive. So if you want to write that positive and negative, I would say to write the positive, so ABCD is somewhere here. There is some ABCDE. They are having some positive shear force. That means this is your positive shear force. And negative shear force for A dash, B dash, C dash, ABCDE dash, they have some value of negative shear force. That you also can show in this way, that you take this section. Here would be some reaction of P by 2. Here is also some reaction of P by 2. If I make that sectional diagram, I would say this is your P by 2. There would be some reaction, and there would be some upwards, in this one downwards, and there is a middle part. And from the other side also, there is some P by 2 upwards. Here would be some downwards, and you take some middle part. You take some one more section that's having ABCD. I will call this one as ABCDE. This one A dash, B dash, C dash. So there would be some upwards. There in this part downwards, and in this part upwards, and in this part also upwards. But there is some vertical load also, so P. So to balance that, there is some upwards on both sides. So I would say this value would be P by 2. P by 2. That's not our part, that how much shear force is there, but concern is that this part. For the ABCD we have positive shear force, and for the A dash, B dash, C dash, E dash, D dash, that is negative shear force. Positive shear force, that means the tau direction, direct shear stress direction is same as that of V direction, as that of shear force direction, but the convention is different for the two. If you make that same direction for the shear stress, this is your shear stress, that is negative shear stress. So that is tau, that is negative shear stress. So for the tau A, B, C, D, E, that is negative. And if you take this one, I would say you have this convention that if the tau is in this direction, that's your positive shear stress, positive tau for A dash, B dash, C dash, D dash, E dash. So to make the final shear stresses on different states of to make the state of stress for these different elements, I would say this is your A. On that there is some because of bending stresses we have some compressive sigma x negative times, yeah, negative compressive. So for that A, I would say there is some negative sigma x. So and on point A there is some shear stress that is 0. Tau is 0 at the top surface, because tau is 0 here, so I would say there is no tau in this part A. So for the part B, for the element B, there is some tau that was your this one, that was your negative tau. So this is your tau for the part 2, element 2, and there is some compressive stress also. So for the part C, it's on the neutral axis, bending stress is 0, but only we have that shear stresses of negative shear stress minus times. So for the part D, it's below the neutral axis, so tensile stresses, that is tensile stresses sigma x, and there is some that negative shear stress also, negative shear stress. For the point E, for the point E, I would say it's on the bottom. On the bottom we have shear stress 0. On the bottom we have shear stress 0. For the bottom we have shear stress 0. So shear stress is 0, but it's on the below the neutral axis, so maximum that tensile stress of m by z. So there is some tensile stress of m by z. That is my max by I. So this is your for those elements on the left side of that load P. For the right side of P, I would say you take point A. It's on the top, so there is no shear stress, but we have compressive stresses. And for the part B, there's some compressive stress also, and there's some positive shear stress also, And for the point C, it's on the neutral axis. There is only shear stress, that's maximum, so that's also positive tau. And for the point D, it's below the neutral axis, so tensile stress, and there's some shear stress of positive tau. And after that, we have element E. There is a shear stress 0, but we have tensile stresses of sigma. So we got these general configuration. That the topic for this one was equals to, the name for this topic was that was your bending stress, and direct, I would say, transverse shear stress, direct or transverse shear stress. This was the combination of those shear stress. Now we are going to take one problem for this kind of combined stresses. Let's have the first problem, that you have this cantilever beam. You have this cantilever beam with subjected to point load at the free end 160 kilonewton, and you take a section at 375 millimeter from the free end. There is some section AA dash, and the AA dash looks like an I section, symmetric I section with the detail is that this was your 20.4, this is your 206 entire depth 206, and the width for the thickness for the web is 7.9, thickness for the flange is 12.6, and you want to say it's given that sigma permissible, maximum stress we can have in the that normal stresses we can have maximum, that is equals to 150 megapascal. You want to check whether any point, let's say this is A, B, C, this is D, this is E. You want to say whether any point, check any point is having stresses greater than sigma permissible. You want to say whether any point is having stresses greater than sigma permissible. So we need to calculate that major principal stress. I would say you need to calculate major principal stress. If you get major principal stress for this section on different points, if I get any maximum stress sigma 1 and then I compare that with this permissible stress, then I can finally conclude that whether there is any point having stresses greater than 150 megapascal. So let's have that. So the condition is that it's already provided to you that what is the section you have to take. Had the question not mentioned that what is the section you have to take, so you have to draw then bending moment diagram, and you have to take the shear force diagram also, and you have to see where is the location of you have to check that shear force maximum location. So this is your case 1. Case 2 is that you have to check maximum bending moment location. So you have 2 cases, and if there is I section also, you have to check at the extreme fibers. This is the first condition, that my by I is there, because you have to check maximum stress at the extreme fibers. And for the shear stress, you have to check at the neutral axis, because tau is maximum at the neutral axis usually, except for the diamond section we have. So you have to check for the so critical conditions is that you have to check where the location of bending moment is there, where is the shear force maximum, and you have to check extreme fibers, and you have to check neutral axis. So these critical points are there. But if the I section is also there, you have to check the junction also, because at the junction we have that sudden increase of that shear stress. So you need to check there also that stresses. So different combinations are there. So for this case, our section is fixed. So this part and this part is directly fixed. So we have to just to see that what is the stresses at these points A, B, C, D, E. But based on the symmetry, I would say that bending stress variation would be in this way, that neutral axis would be at the point C. So stresses at the C because of bending would be 0, and stresses would be maximum at A, and at the B there would be lesser stresses as compared to A. So we have only 3 points. Based on the symmetry, I would say this is your if the bending moment diagram is negative, so it's having tensile, bottom is having compressive. So I would say that magnitude of sigma A is equals to magnitude of sigma at the point E. So I would calculate only sigma A and sigma B for the normal stresses, and for the shear stresses, I would say the variation would be in this fashion. Some sort of variation would be there. If I calculate only tau at the neutral axis and tau at the junction, this part, if I calculate tau at the junction, this value, then I would say tau at the A is equals to 0. Similarly, tau at the E is equals to 0. And I would say if I calculate only this point and only this point, similarly only this point and only this point. So let's have those 4 values. Then I would apply that principal stress equation. So let's have that equation. I would say what is the moment developed at the section AA. So what is the moment at the section A? That's 160 kilonewton into your 0.375 meter. So you got some moment of M. And there is some shear force at that section. The shear force at that section would be equals to shear force upwards. So it would be some value of 160 kilonewton. So we got the 2 values. Now you want to say what is the bending stress at A? What is the sigma at A? That would be equals to bending moment 160 kilonewton into 0.375 meter. So this is your M. What is the Y? That is Y max. So Y max would be equals to 206 by 2. That's that's D by 2, I would say. So 206 by 2 and divided by I, neutral axis. What is the I about the neutral axis? If you calculate that, what is the value of I about the neutral axis? What is the value of I about the neutral axis? So we have a bigger rectangle of 20 point. Is it 204? Yeah. This is your 204 mm. This is your 204 mm. So this is your 204 mm. 204 into 206 cube by 12, and you subtract the those smaller rectangles, this one and this one. And so I would say 204 minus 7.9. This is your B, and D cube. D is the difference of those 206 minus 12.6 two times. 12.6 two times. 12.6 into 2. And this is your cube by 12. And you solve that I value. That I value is already provided to you. The value of I is already provided to you. That's 52.7 10 to the power 6 millimeter power 4. And value of Z is also provided. That's I by Y max. I by Y max is also provided to you. That's equal to 512 into 10 to the power minus 6 meter cube. So these two values we have directly provided to you. So then I would say stresses at A would be equal to my by I, or directly I would say that's m by z. So value of stress at A is equal to 117.2 megapascal. So I got the value of stress at the point A. Now I would say, what is the stress at the point B? Stress at the point B is a linear function of my by I. If I say that stresses at B would be stresses at A divided by, it was for the length of 206 by 2, but I need for the length of only this part. That is 206 by 2 minus 12.6. Or you can directly use the equation my by I. So you can get the value of stresses lesser than the stresses at A, that is 102.9 megapascal. 102.9 megapascal. Now I would say, what is the stresses at the neutral axis? Sigma neutral axis, that is 0. So we got the three different conditions, that sigma A, sigma B, sigma C. Now I would say, what is the tau A, tau B, tau C? I would say tau at A equals to 0 because there is no area above that point. So tau A equals to 0. Tau B is equals to area above that point is a rectangle of dimensions 204 and 12.6, and its centroid is somewhere at a distance of 206 by 2 and minus 12.6 by 2. This is your y bar from the neutral axis. So I would write some shear force of, what was the shear force there? 160 kilonewton. So I would write 160 kilonewton area into y bar, 204 into 12.6 into your y bar, that is your millimeter cube, divided by value of I is already provided to you. Value of I is your 52.7 10 to the power 6 millimeter power 4, and divided by, what is the width I had to take? I know that at the junction there are two values of that stress, shear stress. So I would say I would ignore this part, that shear stress at web at the flange in the junction. I would say that's smaller. I would say, what is the shear stress at the junction but in the web part? That is major stress here. So I would say sigma B at the web. So that means you have to take width of the web at that section. So you need to take B at that. I have to take this width as BW. So width at that section is 7.9. So that is your 7.9 millimeter. So I can get the shear stress at B, that is equals to 95.5 megapascal. Now I would say, what is the shear stresses at the neutral axis location? I can also solve that one also. What is the shear stresses at the neutral axis? Here we have sigma equals to 0. There is a less chance that sigma would be maximum here, that sigma principle, because your sigma is already 0, sigma by 2 plus minus root of sigma by 2 whole square plus tau square. So you are already you have only this value here. So there's a less chance that sigma would be major here. Let's have that still. Let's calculate that still. I would say tau at the neutral axis is the VA y bar by IT. So your area is we have that T section about the neutral axis. So there's some centroid, thickness of 12.6. This is your thickness of 7.9, and depth of this one 10206 minus 12.6, and this part is your 204. So I can solve that. The shear force was 160 kilonewton, and area into y bar, I would say 7.9 into some value of 206.12.6, 206 minus 12.6, and its centroid is at, you can calculate that's at 96.71. This value is 96.71. Centroid is at What is this value? Actually this is 206 by 2. This is 206 by 2, so this is your 206 by 2 there. And if you solve this part, I would say this value is equals to 206 by 2 minus 206 by 2 minus 12.6, that's 90.4. So this value is 90.4, this value is 90.4, and so its centroid would be at 90.4 divided by 2 about the neutral axis. And similarly for the upper area, would say that area is 12.6 into width of 204, and it would be acting at 90.4 plus 12.6 by 2. So you got this AY bar, and you divide by IT. The value of I is already you know, and thickness at the web, that is 7.9. So you can get the value of shear stress at the neutral axis, and that value is equals to 107.92 megapascal. Now we got those tau and sigma at different locations. Now our problem was that you need to calculate whether any points having stresses greater than sigma permissible. So if I now calculate that sigma principal stress at location of A, that is equals to sigma at 1 divided by 2 plus minus, let's forget that minus, I would say sigma 1 by 2, then sigma 1 by 2 whole square plus tau square. So if I use that, what is the sigma at the A? Sigma at the A, that is 117.2. 117.2 divided by 2 plus similarly 117.2 minus 0 divided by 2 whole square plus some value of tau. Tau here is 0. So finally you got a value of 117.2 megapascal. So stress, so major principal stress at the point A is this value. That is, and if I compare that, that is lesser than sigma permissible. That is lesser than sigma permissible. So this point is safe. Point A is safe for this given loading of 160 kilonewton. So this point is safe. Now I want to say what is the point stresses at the point B. Let's have the stresses at the point B. Let's have the stresses at the point B. Stresses at the point B. Stresses at the point B. I would say a major stress, major principal stress at the point B, that is equals to, what is the stress at the point B? That is 102.9. So I would say 102.9 divided by 2 plus 102.9 divided by 2 whole square plus some value of tau at the point B. What is the tau at the point B? That's 95.5 megapascal. 95.5 megapascal whole square. So I got a value of that sigma 1 at B, that is equals to 159.9 megapascal. I would say that's greater than sigma permissible. So your structure is going to fail because your point B is having stresses greater than a permissible stress. So structure can yield or it can fail. I would say there is failure of that material. Then if I take that, what is the stresses at the point C? That is stresses at the sigma 1 at the neutral axis, that is at the C. So I would say that we have the normal stresses 0 by 2 plus 0 by 2 whole square plus some tau value. Tau value was equals to some value of tau that was maximum 107.92, but your normal stress is 0, so overall value is equals to 107.92. So it's lesser than sigma permissible. So this point is safe, but your point at the junction, that's facing that issues. Its stress is having more as compared to that permissible. So your point B has failed. Now let's take one more problem. I would say you have some prismatic bar ABC prismatic bar. That means cross section remains same throughout the length. So you have some simply support beam for the length of 20 meter and subjected to UDL, and there is one more 1 meter here. 1 meter is also there. That's overhang. So the entire length is subjected to UDL of 10 kilonewton per meter. So let's say that this is A, B, C, and I would say the problem is saying you need to get say what is the sigma max anywhere. Calculate the maximum principal stress anywhere in the beam. What is the maximum stress you can have anywhere in the beam? The beam is a the beam cross section is an I section, symmetric I section with the dimensions of 150, 10, 10, and this is also 10, and the overall width, that is overall depth is 300, and this part is 280. This part is 280. So let's have this problem. Let's have this problem. So the conditions for the we have that sigma. We need to get sigma. That is sigma by 2 plus that sigma by 2 whole square plus tau square. So you need to say what is the shear stress and tau at the different points. So we know that for the I section we have 3 critical points. That's A, B, C, D, E. But if the structure is symmetric, if the section is symmetric, we say that you calculate for A, B, and C only. That's at neutral axis, at the junction, in the web, and at the point A. So we are applying. So let's have the but we are not provided with the section, so we don't know what is the value of moment at any section. So we need to draw BMD and shear force diagram. So let's have that shear force diagram. I would say the reactions are directly provided to you as 99.75, and the reaction here is that has developed, that is 110.25. So if you draw that shear force diagram, that would be in this fashion, 110.25, and it would be a linear variation, and here the shear force would be 10 into 1, that's 10. So the shear force diagram is in this fashion, negative, positive, positive. So it's cutting at somewhere here. Let's call it a point D. So we know that at the point where your shear force is 0, dm by dx, that is 0. That means m can be a maximum value there. So there's a possibility that moment is maximum here. And if I draw the BMD here, I would say bending moment diagram looks like a maximum here, and then decreasing to some value such that the value here is 5, and here the value is some value of 497.5 kilonewton meter. So I would say you have to take the sections where I would say, so the critical sections we have, critical, that's your D for the bending moment for BMD, and section that's B, section B for the SFD. Section B and section D are critical because shear force is maximum at the point B, and bending moment is maximum at the point D. So we need to use those values in the equation. So bending moment diagram is positive. That means top fibers having compressive, bottom tensile. So if I draw that diagram, I would say the critical M is that sagging bending moment. Critical moment is sagging, so top compressive, bottom tensile. So point A is having tensile stresses of M by Z, and this one is having My by I, and this is 0. So stresses, so we have 3 critical points, A, B, C. So we got the stresses. And if we talk about the direct shear stresses, if we talk about those stresses, direct shear stresses, it's maximum at the neutral axis. So tau C, and there is some value of tau B also, and there is some value of tau A, that is 0. So so our tau A is 0. Okay, tau B is some value, we need to calculate VAY bar by IT, and tau C is maximum, so that value is also we need to calculate VAY bar by IT. So we need to solve those 2 values, and similarly from this one we need to solve 2 values, M by Z and My by I. So let's have those values. Let's take those values. I would say let's take that value. So one thing is that this one is the general condition that you have to take. But if you analyze the problem now, let's have the analysis of the problem. You would see, you would get amazed at how the problem was actually designed. Let's take the stresses at A for the maximum bending moment. So I would say stresses at A would be equals to some bending moment value of 497.5 kilonewton meter, and value of Y would be Y max. What is the Y max we can have? That's 140 plus 10, then that's 150 millimeter. And I, the value of I would be equals to, as we know how to calculate value of I, That's 150 into 300 cube by 12 minus some value of 150 minus 10 into some value of 280 cube by 12. So you got this value of I, and that's your my by I. So stresses at A, that is equals to 916.844 megapascal. And if I want to say what are the stresses at B, I would say that is equals to stresses at A for the length of 150, but I need for the length of 140. So stresses at B would be equals to this one is your 140 and this is your 150. So accordingly, I can have linear variation. So I got the stresses at B equals to 855.72 megapascal. Now, I would say what is the stresses at C? That is stresses at C, that is neutral axis, that is 0. Okay. Now we are talking about the shear stresses now. Corresponding to the same. See the difference between the previous problem and this problem. We say in that previous problem we had corresponding to that location of bending moment. When we cut that section A, there was some shear force and there was some bending moment also. So we would say there was some bending moment, there was some shear force, and for the same section you were calculating the stresses. So for this case, once you took that critical condition for bending moment, you have to take that same particular section in the element in the beam. So you are analyzing this section now with the points A, B, C, D, E. So this section, same section, you have to take same shear force at that section. So shear force at that section is equals to 0. So I would write, since shear force is 0 at that section, I would say section D. So your tau is 0 at all points in this one, because your tau is equals to VA y bar by IT. Your V is equals to 0. Since the shear force is itself 0 in this equation, so I would say tau is 0 at all points on the section D. So if I say what is the major stresses, principal stresses, now I would say sigma 1 at A, that is directly I would say that's 916.844. And if I say sigma 1 at B, that is also 855.72 megapascal. So stresses, these are your major principal stresses on those two critical points. Now if you want to take next critical section, that's your section B, where we have section shear force of 110.25. This is your just to the left of that support B. So your next section is that critical section is that section of B, just to the left of section B. So if I take that, I would say at the section B, I would say at the section B there's some shear force, but the bending moment is lesser, so 5. If I calculate the stresses because of that 5 kilonewton meter, that would be lesser. So I would say stresses at the section B, if I calculate based on this variation, I would say stresses at A, tau at A equals to 0. Tau at B would be some value, but tau at neutral axis would be maximum. If I calculate this part, and I would say stresses at mid is 0 because of that M equals to 2 kilonewton meter, 5 kilonewton meter, this one. So I would say this is negligible as compared to the tau you had developed. So comparing 497 with respect to that 5, I would say the stresses at section B would be lesser. So still I would calculate tau at the neutral axis, that is equals to that would be equals to that. If I calculate that based on this one, I would say AY bar for this section, that dimensions of that section is equals to 140. This is your 10, this is your 150, and this is your 10. So if I calculate the AY bar about the neutral axis for this part, so AY bar I would calculate that 140 into 10, centroid at 70 plus second area is 150 into 10, centroid is at 140 plus 5, 145, divided by INA. I have already calculated that INA, that INA. So you use that value of I, and what is the width at that section, at the neutral axis? That is 10 mm. So you get the value of tau at the neutral axis, that is equals to so if you compare this value of tau, because stress is 0, that means your major principal stress is minor principal stress, that is 38.86. That's 38.86. That's 38.86. So that's very less as compared to that 916. So your maximum major principal stress anywhere in the section is anywhere in the beam, that's 916.844 megapascal. So you can also calculate for the point B, that's at the junction. At this point also you can calculate for the section B, you can calculate there would be some area of this one, and there it would have some shear stress of lesser than 38. It would have some shear stress that is lesser than 38. Let's say there is some shear stress of 25, and there would be some value of my by I. There would be some value of my by I, because your m is smaller, that is 5 kilonewton meter. It would be some value, but overall value, final value would not be more than that 916. So you can say major principal stress in the beam is that sigma 1 equals to 916.844. That's also at the section DD. At this section we have major principal stresses of 916.844. Now next part of this combined stresses is that we have next part of that combined stresses is that we have the concept of that combined torsion and moment, combined torsion and bending moment, combined torsion and bending moment. Let's take that one. So I write that topic. That's your combined bending and torsion. So combined bending and torsion, So there's some bending moment, there's some torsional moment. So let's have that shaft. And there are some points on a particular cross section, on a particular section, that say this is some point A, this is some point B, this is some point C, this is some point C. These points are on the surface, and this is your D. So your points A, B, C, D are in this fashion, that this is your A, B, and this is C, this is D. So they are on the surface of that section. Now this section is subjected to the torque of T. That's your clockwise torque, and it's also subjected to bending moment in about the Z direction. So there's an M. Let's say the direction of M is clockwise, M in the Z direction. So this is your Z, this is X, and above this is Y. Now we have to combine it. We have combined stresses here. Let's talk about the M. Let's talk about the M first. I would say there's some M here, and there's some M here. Development of that moment would be here. So it's a hogging bending moment, hogging curvature of the beam would be there. So top members, they have tensile, bottom compressive. So it would have some shape of in this fashion. So I would say bottom compressive, top tensile. So we have some values of my by I. So if I have this section now, if I take this section now, I would say for the point A, you have tensile stresses. I would say for the point A, sigma 8A would be equals to some value of my by I, that is equals to 32 m by pi d cube, the direct relation we have. And stresses at the B is equals to stresses at the D, because both the 2 points are on the neutral axis. They are on the neutral axis. So this is your some neutral axis here. So B and D are on the neutral axis, so stresses would be 0 at B and D. And if you take stress at the point C, that's below the neutral axis, and it's having compressive, so minus value of 32 m by pi d cube. So we got the stresses because of moment. That's easy to calculate. Now talking about that torque. Now talking about that torque. Let's talk about that torque. Let's talk about that torque. So let's keep these to side. Let's keep these to a side. So we have this done. That moment is done. Moment is done. Let's remove the moment. Now we are talking about that torque. So for this one torque, for the torsion, we say you go left to right. You go left to right. You go from left to right. Then you cut the section. You cut the section. Then the stress you show on the right plane. You show the stresses on the right plane. Show the stresses on the right plane. So we don't know the we know that because of torsion there is that shear stress because of torsion. But the thing is main concern here is whether the tau is negative or positive. This is your main goal here. So for that we say you go from left to right, and you cut the section and you show the stresses on the right plane. And based on that we say that in the for the sign conventions, for the sign convention we said upwards tau is positive, and in the positive x we have this positive tau, and in this side we have tau that z positive. So tau is positive in this fashion. Upwards, if the tau direction is upwards, the tau is positive on the right plane. We are talking about the right plane. And x we have positive in this fashion, and z, if this arrow is away from that that plane, so tau is positive in this fashion. So let's have that. So I would say I'm going to make a line diagram for this torque. So your torque is anti-clockwise. So torque is anti-clockwise. So thumb points away from the section. So thumb points away from the section. So thumb points away from the section. And here at the support it would be up in the opposite fashion. So at the point that at the support side there is some torque that's in this way, clockwise. So I want now. So I had to take the section now at this point. So I want to say what is the resisting torque here. So if I take that section, there is some T, and there is some resisting torque of in the opposite direction. I would say this is some T resisting. So this part, the direction of the T resisting is critical here. So you have this resisting TR in this way. How can you make this TR in this way? So that means there is some anti-clockwise torque developed, anti-clockwise torque such that the point thumb points away from that support fixed side. So that means here the arrow is in this fashion. That's anti-clockwise about the polar axis. So this is your T resisting. Now if you have this section now, A, B, C, D. So I would finally say that there was some section of A, B, C, D, and the torque, resisting torque is in this fashion. Resisting torque is in this fashion, TR. TR is in this fashion. See, arrow, actually the arrow is opposite here. If I see, do you see this arrow? Where it is pointing? It's pointing clockwise about the polar axis, isn't it? It's clockwise about the polar axis. So actually the there was some error here. So finally let's take that this as a and I would take it this in this fashion. Let's say the T was in this fashion. Let's say the finally we have developed this sense. So let's say the T is in this fashion. So T is the direction of T is anti-clockwise about the polar axis. So thumb points away from the section. Initially the moment was clockwise, so it should have been towards the section. But and as of now, let's take the direction. Let's change the direction of that T. So finally I would say T is anti-clockwise, and point that direction of that T is away from the section. So rest of this is okay. So there would be some resisting torque in the opposite fashion. So finally we said there is some T in this fashion. Resistance would be opposite. So you take this section at some value of x. There is some resisting torque in the opposite fashion. So this one would be some torque that's in anti-clockwise manner. So you have this one in the anti-clockwise manner. This is your point A, this is point B, this is C, this is D. Now we have 4 points, and our critical thing is that the direction of tau is in the direction of TR. Direction of tau because of torsion is in the direction of that resisting torque, because direction of tau will be in the direction of resisting torque. So there will be some, and that's tangential, we know that's tangential, that's tau tangential. So this is your tau direction. So if you take that those 4 points, I would say that's your point A, and this is your point A, okay, and the direction is that in this fashion. Direction is this one. So I have to take on this plane direction in this way. So we got this tau, and you take that another element that you take the other element that's your element B. On this one we have direct downwards of tau, downward tau. Similarly for the point C, for the point C, you have that direction of tau is in this way. This is your tau. And for the point D, we have direction in the way of upwards. So we have this upwards tau. And if you combine them with that of what we call as we already have those stresses because of those. So if I have these one, I would say this is your A. On this one there is some tensile, and for the point B and point C we have 0 stresses. And for the point C we have compressive stress sigma. So then we have to combine those. Now we don't know whether your ABCD is having tau positive or negative. So for that we have this condition that this is your positive for the tau. Our convention is that this is your positive tau in the Y, this is your positive X, and this is your positive Z. So if the arrow is in the Z direction, but it's towards the positive Z, so your tau is positive. So your tau is positive tau. And this one is in the Y direction. Arrow is in the Y direction, but it's downward, so I would write minus tau. So this is your minus tau. And for this one, we have arrow in the Z direction. Arrow is in the Z direction, so I would say minus tau. Arrow is in this that you can write arrow. The direction of arrow is in. You can write positive or negative. Accordingly, you can say. Accordingly, you can write. And for the point D, direction of tau is upwards, so positive Y, so tau is positive. So finally you want to combine those tau and sigma. So let's combine those tau and sigma. I would say there's some point A. On this one we have some tensile stress of sigma in the X direction, and we have tau of positive tau. How can you write the positive tau for the plane stress condition? You have that tau in this way. So this is your positive tau because of torsion. And for the let's have all those points B, C, and D. I would say for the point B and C, for the point B we have stresses sigma 0. For the point B and D we have sigma 0 because they are on the neutral axis. For the neutral axis points on the neutral axis we have sigma 0. So B and D is having stress 0 for that sigma, but they have tau value of. For the point B we have tau value of negative. That's value of tau negative. That's in this way. This is your tau, that's negative. And for the point D we have positive tau. This is your positive tau, positive. And for the point C we have compressive stress of that minus 32 m by pi d cube. So sigma for the point C we have minus sigma, that's negative. And we have some shear stress that's also negative shear stress. So negative shear stress. This is your minus tau. So we got the general configuration. Then we say you take any element that's having those combined effects. Let's have that point A, which is having both the effects. That's having some sigma also. That's having some tau also. So I would say for the point A, there's some major principal stress and minor principal stress. I would calculate that as some value of sigma by 2 plus minus some value of sigma minus 0 by 2, because your sigma in the y is 0, but sigma in the x is some value sigma and plus some value of tau square. So I would say what is the value of sigma? The value of sigma is equals to 32 m by pi d cube, and you divide by 2 plus minus. Similarly, you have there 32 m by pi d cube and divided by 2, and you square it, and plus what is the value of tau? Do you know what is the value of tau? That's 16t by pi d cube. 16t by pi d cube, that's whole square. And if you take that 16 by pi d cube as a common term, 16 by pi d cube as a common term, you are left with m plus minus m square plus t square. So you got this general equation that you can write sigma 1 comma sigma 2, that's equals to 16 by pi d cube m plus minus root of m square plus t square. So you got this equation, general equation, and you want to say what is the tau max we can have? Tau max we can have that 16 by pi d cube and m square plus t square. This part, m square plus t square root. So you got this part. And now we have this concept of what we call as equivalent torque or moment. Equivalent torque and equivalent moment. Equivalent moment and equivalent torque. ME and TE. We say that the effect of those that we say the stresses. This is the concept that if you're talking about what is the ME, it's that value of M, that value of bending moment, If this is acting alone, it would cause same major principal stress sigma 1. That is equals to as caused by, I would say, as caused by the combined effect of torsion and moment. So because of the T and M that was acting on that element, I would say they have contributed some value of sigma 1 that was equals to 16 by pi d cube m plus root of m square plus t square. And if I use that, if I apply only that value of bending moment alone, that would cause same amount of principal stress sigma 1. So that's your equivalent bending moment. So if I say there's some value of m, E, it would cause some bending stress of 32 m E by pi d cube, and that's also equals to sigma 1. That's caused by combined effective. We know that sigma 1 equals to 16 by pi d cube m plus m square plus t square. So we can write the equation for that. What is the equivalent moment you can have? That equivalent moment you can apply, that's equals to m plus m square plus t square, because we are talking about the major principal stress. So this is your equation. And similarly, we have that next topic of equivalent torque. That's T equivalent. So this is your amount of torsion or torsional moment. You have to apply alone applied. This is alone applied. If you are applying only this amount of torsion, and that's your TE, such that it would cause same amount of tau max as contributed by that combined effect of that 16 by pi d cube and that m square plus t square. So if you have this one, if you have this TE, it would cause that tau max equals to that effect as caused by that combined effect. I would write 16 TE by pi d cube, that equals to 16 by pi d cube m square plus t square. So I would write equivalent torque equals to m square plus t square root. So this is your equivalent torque, m square plus t square whole root. And you got these two concepts. Now we take the problem now. Let's have that problem now. So let's have that problem. This is a beautiful designed problem. Let's take the problem. You can learn a lot of stuff from this problem. So we have the shaft attached to some side. I would say this is some fixed side. We have some shaft attached to the side support, whatever we have, a wall and anything we can have. So then after that we have this section, and to the center we have attached some plate or a bracket. We have attached a bracket that's in the z direction. So this is your z direction, and this is your x, and this is your y. So we have placed the bracket plate in the, and that's what we call as z direction, and its value, let's say this value is a, and value of a is equals to 50 millimeter. Now you are applying loads. You are applying two different loads. One is load in x direction at the tip of this bar, P in the x direction, that is equals to 15 kilonewton, and you are applying one more load that's upwards but in the y direction. So P in the y, that's equals to 18 kilonewton. So imagine that you have the shaft, you have the shaft, Let's say this is your shaft. This is your shaft, and you're attached that plate. Now you are applying on this plate. You are applying a load in y, and you are applying load in x direction, and plate is in the z direction out of the plane. Let's take that. Let's take the problem. So let's analyze that. So we want to have those loads onto the center, because if you transfer the loads onto the center, there might be development of those moments and torques. So that's what we have to check here. So let's analyze that. And the problem is that, so that part you have to do, that you have to see the effects of those moments and that loads. But the thing is that you need to get, there is some point K on the surface, some point K along this point. So let's say there is some point K on this line. So at this section, there is some point K at a distance of 60 millimeter from the free end, and there we need to calculate the tau at the K, the shear stresses because of that on that particular K, and normal stresses at the K, and then you calculate major and minor principal stresses at that K, and tau max at that point K. So these things you need to calculate. First you need to calculate tau at K, sigma at K, then principal stresses and tau max. So this is all you have provided with. And the diameter, we can say the diameter is equals to 40 millimeter diameter, 40 millimeter phi of that shaft. Now let's take the effect of the, I would say, let's take the bending moment first. Bending moment. I would say this is your plate in the z direction, along the z direction, and you are applying load in the x direction, px. So there might be some value of px here, resistance, and because it's trying to bend this bar and bend this bar about which axis is trying to bend this bar. So if you have this bar, it's trying to bend it about this axis, that's above that vertical, I would say vertical axis, y axis. So it's trying to bend it in y axis. If you have this y axis, so there is a moment developed about the y axis. There is some moment developed about the y axis in this bar my. So moment developed about the y axis, that is equals to px into some lever of a, so pxa. So you got my equals to pxa, and that same value of my would be transferred into this shaft. You have the shaft now, and this is your y axis, and same effect will get transferred. Here it was clockwise, and in this part we are having said that what we call as anti-clockwise. How can you make the anti-clockwise? I would say this is anti-clockwise. Here it was clockwise, this is your clockwise, and in this part it would be anti-clockwise. And similarly, there would be some resistance provided by the fixed sides, there is anti-clockwise. So I would say this is some sort of sagging bending moment, but the thing is that if the bending moment was about the z axis, if this was your z out of the plane, then the neutral axis, we know that neutral axis is along that mid. If you had this section, then neutral axis would be some sort of this one. But in this case, bending moment is about the y axis. Bending moment is not about the z axis. So bending moment is not about the z axis. It is about the y axis. So this is your my, and that means your zz would be zz would not be your neutral axis, but y would be your neutral axis. So your neutral axis would be y. So this would be your neutral axis. So based on this one, you need to say what is the stresses at this point K. That is somewhere here. So I would say this is your section. Neutral axis is this one, y. This is your y neutral axis, and point K is here. and you are applying that sagging bending moment. That means your point K. If you are applying sagging bending moment, that means point K is bottom, point K is downwards. So that's getting that tensile stress. So point K is getting tensile stress. So I would say the stresses at that point K because of My, that's tensile stress. So I would say that if this is your neutral axis, that means bending stresses about the point K, that's your tensile stress or positive tensile stress. So I would write that is equals to My, and what is the value we can take? This one, that's some value of Z max. So that's your value of I would say d by 2 and divided by pi d cube, pi by 4, pi by 64 d to the power 4. So my z by Iyy. So this is your moment at that point. Now the thing is that once you transfer the effect of that moment, now the load is also getting transferred to the axis, so that px is also transferred to that axis. So if this was your section, and the bracket plate was here, you applied px here, and the same value of px would be a transfer to the center px. So there would be if you draw that axial force diagram, that would be a compressive stress diagram minus times. That means the stress at the point K, that is stress at point K because of axial force, that's equals to minus times some value of px by a, that's px by pi d square by 4. That's your minus px by pi d square by 4. So you got this stress also. That's normal stress along the x-axis. Now you got the stresses because of that px. So your px is over. So your px part is over. Let's remove that px part. Now we are having only that py effect. So load is in the y direction, and that rod is in the z direction. Rod is in the z direction, load is in the y direction, and if there is some load in the y direction, there is some moment developed that's in this way, such that it would resist that effect of bending. So there is some moment, and that moment is actually about the x-axis direction. Some moment x, I would say moment in the x direction, that's some torque of tx. So torque tx equals to py into some value of a, p by a. So your moment equals to moment in x that has developed, that is along the polar axis actually. So if I have that effect on that shaft, I would say this is some shaft, Now there's some polar axis. Now actually that if we see that bracket plate is attached such that now it would try to rotate it in this way. It will try to rotate about that shaft in this way. Now if I had that effect, that's your anti-clockwise moment that on that section. Anti-clockwise moment. It's trying to rotate it in this way. Okay. So that means your moment developed would be anti-clockwise, or we can say twisting moment would be anti-clockwise. So you can have that arrow. You can show that arrow also here. So that's your anti-clockwise in this way. So if I make the line diagram, I would say there's some t acting here. That's your t in the x direction. And based on that side, we have that this side is your fixed side. So I would say there's some opposite to that there's some t. And now our concern is that the section t at that point K, this is your point K, and we need to cut that section because your convention is that you go from left to right, and you show that stresses on that right plane. right plane. You show the stresses on the right plane. Otherwise, your stresses, you can get the value of stress. That's easy part, that 16 by pi d cube. But that's not your goal. Your goal is that whether the stress is positive or negative, because you have combined effect of that, because there is tau also acting here. Tau because of directly here. It might be positive. Let's say this is positive because of VQ by VAY by IT. If this is positive, you have to ensure that whether this is positive or negative. Otherwise, that equilibrium would not be maintained. So this is the concern here. Now, let's take that now. Let's take that now. You cut the section at the point K, from the left to right. I would say there's some T. So your resisting torque at that location of, so your resisting torque at the point K, that's your resisting torque. So that means, how can you show this point in terms of arrow? This arrow in terms of that clockwise or anti-clockwise. So I would say the point is, the thumb is pointing away from the section, so that means there should be some anti-clockwise resisting couple, anti-clockwise. So if you have this section now, this is your A, B, C, D, this is your point K. So on that point K, I would say this is your point K. On this one, we have anti-clockwise, that is your T resisting. Now the direction on that point K, tau direction would be in this way, downwards, in the direction of T, and that's tangential. So tau at K, if I have that element, this is your element K, and on that I have to show the direction downwards, tau direction. This is your tau T, I would say tau T. Now if I have to represent it in terms of that plane, I would say this is your point K. On that you have to show downwards tau. That means negative tau. That means negative tau. Tau is negative. And that tau, because of torsion, is negative. That is minus 16 T by pi d cube. And T is about the x direction. And value of, you can calculate the value here also. Let's forget the value. Now the thing is, you transfer the effect of that Py as a moment, or we can say as a torque on the shaft. But its effect is also there. Its effect as a value, as a shear force on this is also there. Now if you have that effect also, so there is some shaft, and you applied, there's some point K here, and you applied at value of P here upwards, that means here downwards, and similarly here upwards P. Finally here P value of Py equals to 18 kilonewton as a shear force from in the upward direction. So moment would be developed about the Z direction. Z direction. That's your MZ. So MZ would be developed. So based on that, we would have neutral axis of ZZ, and point K is on the neutral axis. I would say bending stresses would be 0 at that MZ Y max by IZZ. That is 0 at the neutral axis. So you don't have to calculate the effect of MZ here. MZ, because point K is on the neutral axis for the MZ moment. So your stresses because of MZ would be 0 on the neutral, because point K is on the neutral axis. Now, but there is one more thing, that is shear force. If you make the shear force diagram, I would say there is a downward. Here the reaction would be downwards, Py. So your shear force diagram is actually a downwards. That's minus 18 kilonewton. So your shear force is negative. And now if I have this section, I would say shear force is everywhere negative. So if I cut this section, you have this shear force negative V. That means the direction of direct shear stress would be in the direction of V. So if I have this now stress element point K, on this you have to show direction of tau in this way, as that of V. So but according to our sign conventions, we say that this tau, because of direct, it is positive. We say that tau D is positive. So that tau D is positive, and you have to calculate at what is this point, where this point is actually, if I have this variation tau, I know that tau is maximum at the neutral axis, and point K is also at the neutral axis. So point K is also at the neutral axis. I would say that value of tau would be equals to 4/3 tau average, and that's positive tau because of direct shear stresses. So I got the different values of sigma and tau, and I have to combine them. If I write what is the total tau, at K, that is tau D plus tau T. So tau D is 4/3 tau average. Value of tau average is shear force, that is V. The value of shear force is I would write 18 kilonewton by value of pi by 4 d square. So you got this value of direct shear stress here, and the effect of torsional shear stress, that is because that's equals to 16 t by pi d cube. 16 t by pi d cube. What is the value of t? That's tx. The value of t tx is equals to py into a. Py into a. That's 18 kilonewton into a value of 50. 18 kilonewton into 50. 18 kilonewton into 50 millimeter. So this is your torque. This is your torque. 16 t by pi d cube. So you got, but the value is actually negative because the tau is negative here. Torsion. Tau is negative. Minus signs. So you have to keep the minus also here. So finally, you write a minus also. You keep the color a different color here. That's minus 16 t by pi d cube. So final value of tau equals to some value of tau equals to minus times, that is your negative 52.5 megapascal. Negative 52.5 megapascal. Now the thing is that you need to calculate stresses sigma at k. One is your direct axial stress. That's your px. What is the value of px? 15. The px value was 15 kilonewton. Yeah. So 15 kilonewton by pi d square by 4. Pi d square by 4 millimeter square. Pi d square by 4. So you got this one, and that's compressive. That's compressive, negative. And plus, because of the effect of my by I, because of the effect of my by I, we have this one. We can write 32 my by pi d cube. 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 Pi d cube. But what is the value of my? We don't know the value of my. The value of my was because of the load in the x direction. So value of my, you write value of my is equals to px into a, px into a, px into a. You write that px into a. I can have that px into a. Value of px equals to 15 kilonewton into value of a is 40. Is it 50 or 40? 50 or 40? 50 millimeter. 50 millimeter. 50 millimeter. So this is your my. 32 m by pi d cube, and this was your tensile sigma. Because of my, that was your tensile bottom, tensile, and because of the mz, I would say, because of the mz, mz is 0, I is also there, izz is also there, but your y is at the neutral axis because it's your at the neutral axis. Point k is at the neutral axis, so mz is 0. So we have that also here. Mz is 0 because point is also on the neutral axis. Point was on the neutral axis. Point was on the neutral axis. This one. Because of the mz, there was some mz, but point k was on the neutral axis. So we say that the stresses is equals to 0. So finally, you got the value of stress at k equals to positive value of 107.4 megapascal. So you got the sigma at k and tau at k. Now you want to say, what is the sigma 1 and 2 at the k? That's, we can write the equation. We can write the equation now. 107.4 divided by 2 plus minus 107.4 divided by 2 whole square plus some value of tau square. The value of tau is equals to, we already calculated that, minus 52.5 whole square. So you can get the value of sigma 1 and sigma 2 and tau at k. Tau max, you can write. Tau max at k. So you got these values. You can write those as equals to 128.8 minus times 21.4, 75.1 megapascal. So you got this problem. You got this problem. Hope you enjoyed this. Hope you enjoyed this problem. Hope you. So let's take one more problem. Let's take one more problem. So we have a steel hollow section. Steel hollow, we can call it as a pole. So we have some steel hollow pole. That is used as a signpost. That is used as a signpost, or I would say this is your support fixed. And once signboard has been attached, one signboard has been attached. So there is some signboard attached here. There's some signboard attached here. There's some signboard attached here. Actually, it's up to the center. We say it should be up to the center. Let's say one signboard had been attached here. Now this is your rectangular, I call it as signboard of dimensions. You have the dimensions that 2 meter cross 1.2 meter, and we call it as an offset, this length up to the end. We call this part as an offset from the central line. This is some central line of that pole. So from that we have some offset, and after that we have a steel plate of, or we can say a board of signboard of dimensions 2 cross 1.2, and there's a pressure, wind pressure is there, 2 kilopascal against the signboard. Now there are 2 points on that. If we have that bottom of that tube, so if this is a bottom, I say there's some point A and there's some point B. You need to say what is the major and minor principal stresses at point A and point B. You need to say what is the stresses major and minor at sigma at 1 and 2 at point A and point B at the base. So if this is your hollow section, its dimensions are in this fashion. If the point A is here, point B is here, so the outer dimensions, I would say D outer equals to 220 millimeter, and D inner is your 180 millimeter, and the height of the steel board from the bottom, that is a signboard, that is 6 meter, and I would say the pressure is acting, let's call this direction as X, this is Y, and out of the plane, that is Z. So that wind pressure is acting, I would say, along the Z direction. So there would be net of that a force would get developed that would act at the centroid of that bolt, center of that signboard. If there is some stress acting, area of that signboard is 2 meter and 1.2 meter. So I'm showing that resultant of that stress into, or we can say pressure into that area, that would give me some force F, and that F is acting as a cross on the centroid of that signboard. So if I have that pressure of what we call as 2 kilopascal, and you multiply that 2 into 1.2, so net value we can get as a net value of force equals to 4.8 kilonewton. That would be acting at the centroid. So cross represents that it's in this way, that it is in this way, in the PZ, I would say. Let's call it as a force in the Z direction, PZ. So there would be some value of PZ. So that's 4.8 kilonewton. 4.8 kilonewton. Now that's acting at the centroid. So if I say what is the net value of that, what is the net height we can have then up to the centroid, H dash, that would be 6.6 meter. And if I say what is this distance now, I would say this distance equals to 1 is your 1 meter, 1 meter plus 1.5 meter. Can we say that this one is your 2 meter and this offset is 0.5? So final value of 1.5 to the center of that section. Now we would see we are going to see that what's the effect of that load in the Z direction at some eccentricity from that center line and acting at a distance of 6.6 from the bottom. So we need to say what is the stresses developed at A and B. So let's take that horizontal effect. Let's take the horizontal effect. I would say there is some load acting here. So a reaction would be upwards. But if I see it in terms of if I see it in terms of that, I would say in the top view, you are viewing it actually you are viewing it in what we call as from the Z direction you are viewing. And now if I want to see in vertical direction, so I would say a load is acting. I would say a load of PZ is acting here, and here would be PZ. That means your moment developed would be here M. And if I analyze that, this moment M that has developed, it would be about y-axis. Why it would be about y-axis? See, if this is your reference line and you are applying a load, you are applying a load. That means if this is your bracket, if this is your shaft, you are applying a load in this way, that this is your x direction, and you are applying load in the z direction. So it would try to rotate the shaft in this way. It would try to rotate the shaft in this way. So that means a moment or a torque would get developed in this way. That's your, if I have the shaft in this way, if I rotate that shaft 90 degrees, I would say a moment, anti-clockwise moment on that shaft is acting. Anti-clockwise moment on that shaft is acting. Anti-clockwise moment. So finally, I would say an anti-clockwise moment is acting on that shaft. If you have the shaft here, I would say an anti-clockwise moment is acting on the shaft because of that PZ effect. So you would see, because of this, about this axis, it's trying to rotate this sine board about y-axis in this way. So a resistance. So we can say finally it would develop in this way. It would develop in this way. A moment, or we can say torque has been developed in this way. So if the moment is developed in this way, that we can call it as a torque. That value of torque equals to Pz into 1.5 meter. So then after that, we had this point A and B here. We had this point A and B here. This was your point A, this was your point B. And now if I want to say, if I want to rotate it now rotate it. If I want to rotate it 90 degrees, let's rotate it 90 degrees. I would say this was your initial. Now I want to rotate it 90 degrees. So I would say this is your configuration of that. So finally, if you want to do it, its analysis, I would say let's remove this part now. I would say. So finally, I would say your point A has reached here, and this point B has reached here, and I would say you are applying an anti-clockwise torque T. So here the resistance would be, I would say T is in this direction, so thumb is pointing away. So there we have in this way, and here we have in this way. That means if you got a section, because we want torque direction, we want torque direction of torque, tau T. So I would say you cut the section. Why do you want? So there would be some resistance. Let's say this was your T, and here we have some TR. We have some TR. Let's say this TR is in this way. So I would say the direction of TR, that means the direction of TR is anti-clockwise in this way. Because if your right hand is anti-clockwise, that means the direction of TR is in this way. So anti-clockwise TR. Now if you take that same circle, now, I would say this is your A and this is your B. On that, your anti-clockwise torque is applied. So I would say tau direction for A is here, and for this tau B, it is this direction. So let's make the element now. I would say this is your element A. Now to make the stress on that, I would say your direction is downwards, so you show downward direction. And similarly for the point B, you have this point B. I would say for the point B, your direction is in this way. This is your point B. So I would say this is your point B, tau. So we got the direction of tau T for A and B. Okay. Now since you had transferred the effect of the torque or moment, now you want to transfer that effect of the load itself. So you are applying a load in the Z direction. So that would be transferred finally here. Finally, that would be transferred on the shaft itself directly. So finally, transferring the effect of that one, I would say This was your shaft. There was some A and B, and your load was somewhere here, and you want to transfer its effect as a load itself on the shaft. So that means if I rotate it now, if I rotate this part now, if I rotate it 90 degrees, I would do analysis in this way. I would be doing analysis in this way. That means that means that means that means that means load is applied in this way. P is applied in this way. PZ. Load is applied in this way. PZ. Now I would say, what is the shear force diagram? What is the shear force diagram? I would say shear force diagram would be a positive SFD. A positive SFD means in this fashion. Positive SFD. But actually that if you see that that load is in the Z in this way, that yeah, load is in this way. Load is in this way. See the thing that the load is out of the plane. Load is out of the plane. Load is out of the plane. That means if you want to make the effect of that, that means that same load would get transferred on the top, on the top, and you have this cantilever, and point A is from the top side, and point B is on the that side of that. So we have this one. This is from the top. This is, you're seeing it from the top, and load is also from the top. Now if you rotate that element, that top load was in the top, and point A has reached to the top. Point A would reach to the top. Point A would reach to the top. It is similar to that. It's similar to that. This is your point A from the top. Load is acting in this way, top from the top. So the point A is at the top, and actually the configuration seems to be in this fashion, that this one, when we rotate it, so when we rotate this element, point actually this is not showing that same direction. Actually the load is vertical. We have to show that the load is vertical. Similarly, this point A is not here, and point A has to reach on the top, because this cross can't define that load is acting vertical for this one when you rotate it. So we have to show that load is vertical, and point A also shifts upwards. If the point A shifts upwards, I'm showing that I would say there is shear force diagram. There is some SFD also. There's some SFD, and if I make that diagram, there would be some that shear force diagram would be there. There would be some shear force diagram also. There would be some shear force diagram. This is your SFD, and it's positive. I would say this is positive. So your torque diagram, your shear force diagram would be in this way. Then your shear stress diagram would be in this fashion. That's negative tau, because of that direct shear stress. And third one is that you got that effect. Now you can have one more thing. We can have one more thing. That's the effect of that that load is acting here at the centroid, and there is some cantilever here, and that means a moment gets developed. A moment would get developed also. A moment would get developed. So you're applying a load in the Z direction, P in the Z. That means you're, if I rotate it, let's rotate it to get an understanding, to get a better understanding. I would say you applied a load in the Z direction. So moment would get developed. In anti-clockwise mz. That is pz into 6.6 meter. So moment z is getting developed, not moment z. I would say moment is getting developed. Moment. So you're applying a load. You're applying a load here. You are applying a load in the z direction. So if I have that, so load is applied in the z direction. Actually, I would say you are applying load in the z direction. That means reaction would be upwards, and moment would get developed about the x-axis. Moment would get developed about the x-axis. So this is your towards the beam, towards that pole. That means moment would get out from the top. That's about the x-axis, moment mx. such that I would say moment mx equals to pz into 6.6. That value equals to pz into 6.6. That equals to what is the value for this one? Mz. That is value of 4.8 kilonewton into 6.6 meter. So moment in x direction, that's a bending moment. This is bending moment. This is not torsion. So bending moment in x direction, that's equals to 31.68 kilonewton meter. So we got the different that moments and that torque and shear force. Now we want to say what are the different stresses we have. What are the different stresses we have? So let's talk about that torque we studied first. Let's talk about the torque. We know the value of that 16t by pi d cube. But if you have hollow section, the section was actually hollow. Actually, the section was hollow. So if you have this one, we have the hollow section, 220 and 180, 220 and 180, 220, 180, 220, 180. So we have the dimensions that one is your 220, next one is your 180, 220, 180. So if I write the equation for this one, I would say this tau is positive, negative. This tau is for A is negative. This tau is negative for A, negative tau. And for the B, this is also negative. This is also negative. For the B, this is also negative because your arrow is opposite. Arrow is in this way. That's minus z direction. So tau B is negative. So I would write for the B is also tau is negative. Tau is negative. So tau is negative. Tau direct for A and B is negative. Yeah, this is tau t. Tau t is negative. What is the value of tau t? Do you know the equation for the hollow sections? That is 16t by pi d outer cube and 1 by 1 minus beta to the power 4. This is for the tau max because we are talking about the surface. So your tau equals to tau max. Now we'd say what is the value of that? What is the value of that? 16 into t. The torque developed was equals to, what is the value of torque? The torque equals to that we have that value of torque was equals to pz into 1.5. pz into 1.5. pz into 1.5. 4.8. pz into 1.5. pz into 1.5 meter. This is your torque and divided by pi. What is the d outer? That is 220 and cube 1 minus beta to the power 4. 1 minus beta to the power 4. 1 minus 180 by 220 to the power 4. And you have this bracket. So you get the value of that tau t at A. Is it A? Yeah, tau t at A equals to tau t at B. That is minus times 6.24 megapascal. 6.24 megapascal. So you got the first stress, where that is your shear stress. Now you would say what is the second value of that direct shear stress? Direct shear stress. We have that equation. We have that SFD. So this was your condition that you had negative shear stress direct. It is negative. And the variation is the parabolic variation. Do you know that parabolic variation is there? Now if your point A has reached to this point and point B would reach to this point, finally I would say on the neutral axis point B is there. So tau neutral axis is equals to tau B and tau A is equals to 0. So what is the value of tau for the hollow sections? If there is hollow section, the equation is that the equation is that you write the equation in terms of we know that if there was solid tau is equals to tau neutral axis is equals to 4 by 3 and v by a 1 minus y square by r square. This was the equation, general equation. But if the section is hollow, we have one equation that is equals to tau at neutral axis is equals to that we have 4 by 3 v by a, then we have r1 square plus r2 square plus r1 r2 divided by r1 square r2 square. Is it plus at the bottom? Plus. It should be plus. So we have this equation. So similarly, your r1 is your r inner and r2 is your r outer. So you can use those values now. 4 by 3, your shear force value was equals to Pz, that is 4.8 kilonewton. And the area of, what's the area of that hollow section? I would say that's pi by 4, 220 square minus 180 square millimeter square. So this is your area. And then after that, you say what is the different values of those R, and yeah, R1 is would be equals to, let's write that as 90 square plus 210, that is 110, 220, that is equals to 110 square, and 110 into 90 divided by 90 square plus 110 square. So you have this equation. Then you write that tau at the neutral axis, that is tau at the B direct, tau direct at the B, let's forget the B, let's write tau D neutral axis, that is equals to 0.76 megapascal. This is the point. For the point B, we have that tau equals to minus 0.76, and for the point A, we have tau equals to 0, because that's at the top. So tau at A equals to 0, and tau at B is minus, because your direction of your tau is negative. So finally, I would write this as tau at the value of tau for the B, and this is direct. So finally, we can say what is the total tau for point A and what is the total tau for point B. So for the point A, I would say total tau for the point A, that is equals to initially I would say tau T A plus tau D A, and for this one I would write tau T B plus tau D B. So that I would say for the tau T, the tau T value was equals to 6.24 negative, 6.24 negative, that's minus 6.24 plus 0, and for this one we have 6.24 negative plus tau dB, that's also negative, minus 0.76, and finally a value of minus 7 megapascal, 7 megapascal for point B, and 6.24 for point A. So we got the shear stresses. Now we want to say what is the normal stresses we have at point A and point B, point A and point B. So point A and point B. So we got some value of moment that was in the Z direction, that was in the X direction. We had calculated that. We calculated that was your why do we really have that? Why do we have that? Yeah, this one. We had this one now. This was our calculation. That moment we developed moment X equals to 31.68 kilonewton. Now the thing is that what is the if you have these 2 points, if you have these points, now actually the point A, from this figure you observe this figure, you are applying load in Z direction. So this is load in Z, this is your Z axis, and I would say this is your y axis, because it was vertical, the member was vertical. This is your y axis, and this is your x axis, so a moment gets developed along the I would say moment gets developed in this x-axis, about the x-axis. Moment gets developed about the x-axis, and there is a anti-clockwise moment. So top would be having tensile, bottom compression. So this is positive and negative. So top is having m by z, and bottom is having minus m by z. So if we have point A at the top, neutral axis is, I would say, this is your element. Point A is at the top, point B is here, and neutral axis is along the x-axis plane, x-axis. So this is your neutral axis, and point A is here. So bending stress would be at point A as a value of my by I, that's m by z, that's positive. So I would write sigma at point A, that's m by z about x-axis, mx by z axis. So what is the value of mx? That is 31.68 kilonewton meter, and we have zx, that is your value of I about the neutral axis. Do you know that value of I about the neutral axis? That is pi by 64, and your outer minus inner, mm power 4, and divided by that's y max. We can have that value here. Value of y max would be equals to 220 by 2 millimeter. and you can get the value of sigma at A, that's positive tensile, sigma at A, that's 54.91 megapascal. And what is the sigma at the B? Can you tell me what is the sigma at the B? Can you tell me what is the sigma at the B? Because your point B is on the neutral axis, sigma at the B is 0 megapascal. So we got the different stresses now. Finally, I would say, what's the major principal stress at point A? That is equals to the stress we have 54.91 divided by 2 plus minus and root of 54.91 divided by 2 whole square plus some tau value minus 6.24 whole square. So we got that sigma 1 at A is equals to some stress of 55.7 megapascal, and sigma 2 at A, that is equals to minus 0.7 megapascal, and tau value, tau max at point A, that is 28.2 megapascal. So we got those stresses for the point A. Now we want to say what is the stresses are for the point B. I would say stresses for the point B, stress 1 comma 2, that is equals to, what is the normal stress we have? I think normal stress we have 0 plus 0 square plus minus 0 by 2 whole square plus tau x square. The value of tau for the B was 7, negative 7, minus 7, and sigma is 0, minus 7 megapascal, minus 7 whole square. So I would say sigma 1 is equals to plus 7, sigma 2 equals to minus 7, and tau max equals to 7 megapascal. So we would say we got those stresses for those two elements. Do you got this problem now? Do you got this what the problem was all about? So let us repeat that problem again one more time. So I would say in this way, there was some steel post, or we can say there was a pole, and it is a hollow section, steel pole hollow section, and there's a point A on the free surface A and point B. So you had some that signboard and attach it at a distance of some 0.5 meter. They were attached here, and there is a wind pressure. So there would be some force acting on this area of that rectangle. So it would act at the centroid. So load is acting in the z direction. So because of this load, it will try to rotate about the y-axis in this way. It will try to rotate. That means a twisting moment gets developed on this point. So this was your line. So twisting moment gets developed in this way. Now, to make this understanding here, I would say this was your point A, this was your point B, and to rotate it now, I would say twisting moment is applied in this way, anti-clockwise, and your shaft is looks like this way, such that your point A reaches to the top. Point A reaches to the top. I think that we saw already we saw that. So that we already saw. So then after that we say that there is some balancing couple here. That means there was some direction of tau in this way, or that balancing torque in this way. Then we say that there is some point A, point B. That means direction is in this way, direction is in this way. Then we got the tau t. Okay. Then the effect of this load on this point as a shear force, So there was some shear force acting here, and I would say the diagram is in this way, positive shear force diagram. That means your shear stress diagram would be negative tau, and value of tau, we had that equation of 4/3 by V by A, some value of R square, R2 square, R1 R2 by R1 square, R2 square. So we got that one also. I would say tau, then we say that tau at A was some value of tau at A was 0 because of direct, and tau B was because B was at the neutral axis. This was your A and this was your B. B was at the neutral axis and tau was maximum here. So we got that tau also. And there was that effect of that bending moment also. A load was acting here, and there would be some bending moment developed about the x-axis, mxx. Then after that we say that there was some point A, point B, and neutral axis was developed along the x-axis, where the point B was already there. So this was your point. This was your x-axis. Point B was here. Point A was from the z direction. So this was your z direction, and point B was here, point A was here. That means stresses would have been developed at the point A. That was equals to my by I, or we can say mx by ixx, and y value was y max, or we can say it was actually z max. So that we calculated that moment also. So these were the total moments we had already. So we had these three different combinations. Then we said total stresses would be equals to, in this fashion that we have calculated. So this was already a good problem that we have. So let's take the final problem from this combined stresses. Let's take the final problem from this combined stresses. So final problem is that we have a lever, ABD. We have a lever ABD. So it looks like an L section, some sort of L section. Now there's some point K, there's some point H, there's some point H here, there's some point H. So there's some point H here, point H. So you're applying a load. So I would say this is Z, this is X, this is Y. You are applying a load in the Z direction. Load in the Z direction. A load of PZ in the Z direction. PZ equals to 600 Newton. And center, I would say the distance here is equals to 450 millimeter. And vertically, the distance here is 250 millimeter. This distance equals to 250 millimeter. 250 millimeter. And I would say the diameter of the shaft, that is 30 millimeter. 30 millimeter. Now you want to say what is the major, minor, tau, that is what is the stress at H, what is the tau at H, what is the sigma 1, sigma 2, tau max at H. You need to say what are the different values of that stresses on that point A, point H. So I would say load is in the Z direction. Its effect would be, let's have the effect about the point H. So let's make a line diagram. I would say you're applying a load in Z. There would be a reaction that's also PZ, and there would be some moment about the y-axis. Moment would be about the y-axis. So that would be moment about the y-axis. That is PZ into 450. So that would be actually torque developed in the long shaft. In this shaft, it would be a torque developed in the opposite fashion, that is in this way. So that moment y would be a torque developed for the shaft, and there is some point H here. So there we have this fixed side, and there's some point H somewhere here, point H, and we want to say what is the torque developed here, and accordingly we can get tau t, we can get tau t. So let's talk about that. So you calculate that my equals to pz into 450. That would be some value of, let's have that value of 600 into 450 millimeter. That is Newton millimeter, and I would get a value of, that is 270 Newton meter. So I got the torque. I would say we have this point A, we have this point H on the top of the surface. We have this surface, and we have that H point, and your shaft looks like in this fashion. Now, if I rotate that, I would say there's some side, there's some fixed side, and point H is at the top. And we are applying torque in this way, anti-clockwise torque T. So I would say to balance it, there a line diagram would be the line diagram would look like in this fashion, and at this section there would be a resisting torque in this way, TR, and its direction would be in this fashion, TR. So this is your TR. So if you have this section now, H section is at the is at the S section is actually this point. This point. Yeah, S section is here. S section is here. So this point H is at the top. So you are looking here. So S section is at the top. So resisting torque has been developed in this fashion. Torque. So this is your TR, and you want to say what is the direction of that tau T. So we know that tau T is in the direction of TR. So there would be some tau T at this point H. So if I have this element H, if I have this element H, I would say the stresses on the right plane, I would say I have to show the stress on the right plane. I would say your direction of tau is in this fashion. So this is your direction of tau. And based on the convention that this is your positive Z, so I would say tau is positive. So tau T is positive. So tau T is positive. Tau T is positive. Tau T is positive. And its value would be equals to, we know the value we know, that's easy, 16T by pi d cube. But that's not the issue. The issue is that whether the sign is positive or negative. 16T by pi d cube. 16 value of torque was your 270 Newton meter, and pi d cube, pi into diameter was your 40. Diameter was your 30 millimeter, 30 millimeter power 3. So you got the tau T, as 50.95 megapascal. 50.95 megapascal. Okay. Now we want to say whether there is any other force that gets transferred. Now see this is load in the Z direction, and on this point if I have, so this load is actually in this way across, so same would get transferred here. If I have this cross here, on this section there would be upwards cross, and if that cross gets transferred to this part, so that looks like a cross on this top, and here it would be upwards. So I would say if I make the shear force diagram, can I make the shear force diagram? I would say this is your section. This is your section. Point H is at the top. Point H is at the top, and load is from the same direction. Load is from the same direction. Now, if I make the shear force diagram, that means there is some point. Load is from the top. That is PZ, and point H is at the top. Now, if you know that shear force diagram variation, what is the shear force diagram variation? Do you know that? This is this, and tau is 0 at the top. There is no need to calculate this point. There is no need even to say what is the shear force sign. That is the shear force positive. Then after that, what is the tau? Actually, the tau here is 0. So you don't have to see what is the shear force here. So I would say tau because of direct is equals to 0. Do you got it? Do you got this point? So shear is over. So total shear of 50.95 is over. Now we want to say what is the bending stress we have. I would say at this point it's at a vertical distance of that we have 250 millimeter. So there would be some a kind of moment is getting developed on this point H. So to balance it, I would say anti-clockwise moment. So let's have that part. So you're applying a PZ in this way, and point H. Let's have that section also. So this is your section, and point H is at the top, and load is also applied at the top. So I had this. If I had this section, if I fix this part, I would say there is some fixed. Here's some fixed beam, and you're applying a load. You're applying a load of PZ, and this is your point H at the top. I would say neutral axis would be in this fashion. Because your circle is there, so there is no confusion. Which should I take? So I would say H is at the top. So a bending moment, that bending stress variation would be in this fashion, such that the bending stress at the top would be my by I. So the moment developed here would be anti-clockwise. Moment is anti-clockwise. That means on the top we have tensile stresses. So positive my by I. And the value of m is equals to, what is the value of m we can have? The value of m you can write here. The value of m we have developed equals to 600 Newton into 250 millimeter. That is equals to 150 Newton meter. 150 Newton meter. So we can have that 150 Newton meter into y. The value of y we can have that's maximum of that's 30/2, that's 15 millimeter, and value of I would be equals to pi by 64, 30 power 4 millimeter power 4. So you can have that bending stress sigma, but the stress that has developed, it's not in the x direction. If you see, the stress is not in the x direction. Why? Can you tell me what is the why the stress is not in the x direction? You don't have to say this is your sigma x. You don't have to say this is your sigma that's tensile in the x direction. It's actually, we are talking about the long axis. We are talking about the long axis. That's your vertical. That's your vertical axis. So we are talking about this point that's acting as a top along this long axis. So if I have this in the with respect to vertical, with respect to horizontal, I would say there's some point H on the top where there is some load also acting PZ. So actually this one, this is your x-axis, and out of the plane, that's your zz axis, zz. Out of the plane, that's your zz axis, and this point is at the top, and your long axis is your y axis. Your long axis is your y axis. Long axis is your y axis. So the stresses developed is because of that moment. We have that bending stresses. That is your sigma y. That's not sigma x for this case. So your sigma x is 0 for this case here. So we say sigma y has been developed. That's my by I. My by I. So sigma x is not there. So sigma x is 0, and sigma y we have that value equals to this one. So we have the sigma y equals to you calculate that sigma y 56.617. 56.617. 56.617. 56.617. Now the thing was that what get the value of sigma horizontal, sigma at h, tau at h, sigma 1, sigma 2, tau max. So we got that tau at h, net value of tau at h. That was the summation of those two. So I would say finally that tau at h would be equals to 50.95 megapascal positive, and tau sigma at h would be such that sigma y is some value of 56.617, and sigma x equals to 0. So if I have that element now, I would say there is some sigma in the vertical, sigma y is 50.95, and sigma in the x is 0, and tau is positive. Tau xy, I would say tau is positive. So there's some tau positive that is equals to 50.95. 50.95, and sigma's y was 56.617. 56.617. Now I can now calculate that principal stresses and their location also. If I write that tan 2 theta p, that with respect to this vertical, I would say what is the location of that principal plane? I would say let's say this is your plane P, this is your plane Q. If I want to make that more circle, I would say you had the two planes, you had those two planes. Plane P is having 0 normal stress and some tau that's anti-clockwise. So some 0 stress and tau anti-clockwise. That means some point here. So I would say this is your plane P, that is 0, 50.95. And there is one more plane Q, with the stresses that 56.617 tensile. So that means somewhere here, and same value of tau. That means this one. So if I join those 2 points, I would be having some line. So the center would be here, C. So this is your O, and you make a circle out of that. Out of that, you make a circle. You make a circle out of that. Let's have that circle. So we got some circle. I would say there's some sigma 1, there's some sigma 1, and there's some sigma 2 also. Sigma 1, sigma 2, and there's some tau max. There's some tau max. I would say this is your plane P, this is your plane Q. And what is the theta location of that principal plane with respect to your principal plane, your plane P? I can call it as 2 theta P1. And if I calculate that with respect to that plane P, there is some theta 2 theta P with respect to the vertical plane where your major principal stress is acting. So if I write that equation, 2 tau xy by sigma x minus sigma y. So I can get the value of that 2 theta p equals to minus 61 degrees. Minus 61 degrees. If I go, that means this is your anti-clockwise 61 degrees. Anti-clockwise. Now if I go clockwise, I would say 360 minus 2 theta p 1 is equals to 360 minus 61 degrees. So I have to go anti-clockwise of. So this is your clockwise actually, but during the derivation we go anti-clockwise. So you have to go at degrees 299. Yeah, yeah. That's you have to go 180 minus. You have to go not 360. You have to go 180 degrees minus 61. That's your 180 minus 61. What is that value? 180 minus 61. That's 119. 119. 119 degrees. 119 degrees. So you need to go 119 degrees. So this is your 119 degrees. And now one more thing is that is 119. Let's take that. This is 190. If I got this minus 61 degrees, this is minus 61 from the plane P. This is your minus 61. That means actually that minus 61 is this part. This part is your minus 61. And if I say what is this value? If I say what is this value, I would say that is 61 minus 360. That is 299. Now if this is 299 and total of that, this part is 180. That means that 2 theta p1 would be equals to 299 minus 180. That's 119. Yeah, this is also correct. Either you do in this way or we do directly. So both ways are correct. So either you go from this plane P, you go anti-clockwise minus what we call as minus 61 degrees. So you would receive sigma 2. Then if you say from the anti-clockwise, if you go to that point, I would say your sigma that theta would be equals to 299 degrees. But if I talk about sigma 1, that would be, you subtract that 180, so you would get a value of that value equals to 119 degrees. So if I say what is the sigma 1 and sigma 2, can you say what is the value of sigma 1 and sigma 2? So you say sigma 1 equals to sigma x plus sigma y by 2, sigma x plus sigma y by 2. So we can write here. So we can write the equation here. We can write here that sigma 1 is equals to sigma x plus sigma y by 2 plus minus sigma x plus sigma x minus sigma 1 by sigma y by 2 whole square plus tau xy whole square. And you can get the value of sigma 1 and sigma 2. Sigma 1 would be equals to 86.54 megapascal and sigma 2 minus 29.94 megapascal. 86 and 29. So we have this one. Let's say this is your 86, some value of 86.54. This one is your 29.94 megapascal. And by the complementary shears, that summation of those stress invariance, I would say stress invariance also, I would say your 56.6167 plus 0 should be equals to these two, 86.54 plus minus of 29.94. That should be balanced also. And one more thing is that tau max would be equals to that root of that sigma x plus sigma y by 2, sigma x minus, that you already know. So tau max would be equals to 58.24. 58.24. So thank you for watching this problem. These problems we have. Thank you. Thank you. Thank you.